For this problem, I want to find the set of all points in R3 such that each one of them is equal distance from P1 equals 1, 0, negative 2, and P2 equals 3, 4, 0. Great, and let's first of all write this set S formally. And formally, it should be all the V's in R3 such that the distance between V and P1 is the same as the distance between V and P2. And for the set S, I claim two things. Claim 1, S is a plane. Claim 2, P1 minus P2 is perpendicular to my plane S. Let's see why. So let's first consider the easier case where my P1 and P2 both lie on the x-axis and are equal distance from the origin. So it means my P1 is going to be some negative a 0, 0. P2 is going to be some a 0, 0. And so why is the set of points that are equal distance from these two a plane? Because if a point V is in my set S, it means I can draw an isosceles triangle from my V to both these points, right? Because these represent the distance. So I can, so along this axis, I can go up and down. I can do this, and so on and so on. So I can go up and down, but I can also go into and out of the page, right? So as a result, this is going to be just the set x equals 0. So everything that lies on the plane that is that is given by x equals 0 is going to be my set S. And now, why is it the case that P1 minus P2 is perpendicular to S? Graphically, I think this is very easy to verify. And rigorously, P1 minus P2, in this case, is just going to be negative 2a, 0, 0. And if V is an S, then it means V is of the form 0ab for some numbers ab. Then V dot P1 minus P2 is just negative 2, is just 0ab dot negative 2a 0, 0. This is 0. Right, so every V in my S is perpendicular to P1 minus P2. So both my claim holds for this very specific case. But why does it hold for my general case? Because I can always translate this picture. You know, I can make it smaller, make it larger, and I can rotate it. I can put it anywhere I wish. So I can rotate and scale it so that P1 and P2 match the P1 and P2s in my general picture. And because I rotated everything simultaneously, both my claim 1 and claim 2, they two still hold, right? Because if you rotate a plane that is perpendicular to the distance, perpendicular to the difference vector between P1 and P2, if you rotate that, this plane is still going to be perpendicular to the difference of P1 and P2. So my claim 1 and claim 2 hold for my general S here. Great. So I can now calculate what is my P1 minus P2 here. for my general case, this is my specific case. And for my general case here, that I'm considering P1 minus P2 is just going to be 3, 4, 1, 0, negative 2 minus 3, 4, 0. And this is just going to be negative 2, negative 4, and negative 2. And since this is perpendicular to my plane S, this is just going to be my normal vector of S, right? So n equals, well, I can scale my normal however I want, equals 1 to 1 is the normal of S. So I have the normal, I just need another point that is on S in order to get the equation for S. But for sure I know that 1/2 of P1 plus P2, which is just the midpoint of P1 plus P2, so it's this point here, it must be in S. Because clearly the midpoint of P1 and P2 must be the same distance from both P1 and P2. So this one must be in S. And P1 plus P2 over 2 is just 1/2 of 1, 0, negative 2 plus 3, 4, 0. So this is 1/2 of 4, 4, negative 2. And so this is 2, 2, negative 1. Great. And so my S is just given by the equation 1 times x minus 2 plus 2 times y minus 2 plus 1 times z minus negative 1, which is z plus 1, equals 0. And this is my answer.